the answer. Bye.
Thank you all for tuning in, and I'm very sorry I can't be there to present this work in person, but hopefully we can still have some interesting discussions about the work in the future via email or Skype or some such. So, brief history about me. I'm Sonali Parbhoo. I'm a postdoc at Harvard University, and I grew up and was born in South Africa. I did my schooling and education, my undergrad and my master's degree in South Africa, so this is very special to me. And today I'll be presenting some work I developed in my PhD for using information bottleneck methods for reasoning about the effects of treatments. And this is joint work with my wonderful collaborators in Basel, Switzerland, Mario Wiese, Alexander Wieczorek, and Volker Rath. So understanding cause and effect is a very important problem across various different applications because it governs how we act. So it determines how we can act in practice. So in the healthcare setting, for instance, consider having a decision problem where I would say, I have a headache and I want to determine, should I take aspirin? Now, the answer to this question depends on the effect that aspirin has on the headache. So if aspirin improves the headache, then I should definitely take it. And if aspirin doesn't do anything to my headache, then I shouldn't. But really, causal inference problems are not just restricted to healthcare, so they are everywhere. In economics, for instance, we might be interested in understanding what is the effect of education on earnings. In marketing, for instance, we might be interested in what is the effect of placing an ad at the top of a Google search and how many clicks will it generate and how much income can we generate as a result. In politics, we might be concerned with what is the effect of involving more women in policy making. And all of these questions have the same sort of flavor of understanding what is the treatment effect or what is the effect of intervening in a certain way. So the gold standard currently for estimating treatment effects is what's called the randomized control trial. Here, the subjects of interest are basically randomly assigned to treatment groups, so treatment versus control for each intervention. And then we measure the effect of the intervention by taking the difference between the outcomes of each group. So if we look at the figure that we show over here, the red patients are assigned to treatment A in this case, and the green patients are assigned to treatment B, and we would observe the difference in their outcomes. And if green responded better than A, then we would know that we would have to take treatment B. Otherwise, we would say, let's take treatment A. What are the problems with randomized control trial? Because there are many. Well, randomized control trials are not always ethically feasible. So for certain problems, when we want to determine effects, we can't always do those experiments in practice. For instance, if we wanted to know if cholesterol causes heart attacks, we couldn't have a group of patients where we elevate cholesterol levels and we observe the effects on their outcomes. Similarly, we couldn't decrease interest rates to try and boost the economy if we were trying to reason about these effects, because it could have potentially catastrophic effects on other individuals. There are several other problems that are associated with randomized control trials apart from feasibility. The most prominent is probably the fact that randomized control trials are conducted over great lengths of periods of time. So for instance, in this coronavirus epidemic, basically, we are waiting for someone to produce some sort of vaccine that would help treat the patients that have this disease. In order for them to, once they bring out some sort of vaccine, in order for them to see whether it's ethically viable and whether it's feasible in practice, they would have to conduct some sort of randomized control trial. They would choose a population of patients that have this disease, they would administer the vaccine, and then they would observe their outcomes. Now, this is typically conducted in a very long stretch of time, so recruiting is typically very difficult. Because it takes a long time, patients might also drop out of the study, and the results that you obtain from that single population might fail to generalize in the long term to patients outside the population. And so we need something else. And so the alternative is really to consider observational data. Now, this is a setting where we have no control over how interventions are assigned. So we have no control over how treatments are administered in practice. Now, the hallmark of observational data is that this data, if we just observe what's given to us, it suffers from various kinds of confounding that typically biases our predictions. So in this example, we might have thought that patients are randomly assigned treatments initially, but upon closer inspection, we see that wealthier patients are more likely to be administered treatment B, and poorer patients receive treatment A. So any difference that we observe in the outcomes is not necessarily an indication of how the treatment is working, but really might be the influence of the actual socioeconomic status in this case. So wealthier patients can afford better treatment and maybe they respond better as a result. And so in this case, socioeconomic status is then a confounder for treatment. And the key goal of causal inference then is to adjust for these effects of confounding in observational settings to reason about treatment effects. So we introduce some notation to develop what's called a statistical decision model for causal inference. So we use the variable or the treatment regime indicator called f of t. Now this is a non-random indicator function. So when f of t is 0, it basically means we are in the randomized control setting where we give no treatment to that patient. So we choose a population, we randomly split it, and then that portion of the population doesn't get the treatment. When f of t is 1, we basically in the randomized regime, once again the interventional regime, where the treatment is actually assigned. And then when f of t is empty, we just basically observe. So we're in the observational regime, not the interventional regime. And t can take on any value in this case. It can be 0 or 1 or some other value, and it's a random variable because we observe what's given to us. So when we were doing or estimating the treatment effects in the randomized setting, what we could basically do is estimate what's called the average causal effect. And this is basically the difference between the expected value of the outcomes given the particular intervention that you have. F of t is 1 or f of t is 0. And geometrically what that looks like is basically looking at the distribution of treated patients versus those that are not treated and taking the difference between the means of those distributions. Now, the ACE is computed in the interventional regime, so the randomized control trial setting. But now we are in the observational setting where we don't actually observe how the treatments are administered, so we don't have access to that mechanism. And so can we do something similar to quantify the causal effect in the observational setting? And this is the key question here. Now, I want to mention at this point that this problem is formulated in this case in the statistical decision theory kind of framework, but there are various related problems that have a similar sort of flavor. And one of those is off-policy evaluation in reinforcement learning. So this is when you're given data from a particular treatment policy, I would say, and then you want to reason about the effects of a different policy in practice. So there is this mismatch between the two distributions. And then also in contextual bandits. And so really what we propose here could be applied in various different contexts then. So it turns out that in the observational regime, it is possible to estimate treatment effects, but this is only possible if we can somehow make the outcomes that we observe conditionally independent of this interventional regime. And how we do that is basically by introducing something called a sufficient covariate. So Y becomes then conditionally independent of this interventional regime, given that sufficient covariate and the treatment assignment then. And if we can compute some sort of sufficient covariate, then we can use this to quantify something called the specific causal effect. That is, the causal effect on the group of individuals that have this sufficient covariate Z. And then the ACE, or the average treatment effect, would be given by averaging over those Z representations or those sufficient covariates to get an average over the population. So the key question then is, how can we learn this Z? And this is what we will be focusing on for the rest of this talk. But before I get there, I want to introduce the main problem that we try to tackle in this approach. And so this brings us to our focus, which is estimating treatment effects now with systematically missing data in medicine. So I'll touch on how this is related to the notion of a sufficient covariate in a second, but I really want you to understand the notion of systematically missing data first before we get there. So in medicine, in practice, what we really want to do is we want to estimate treatment effects, but we have this high-dimensional data that we get at training time. And this can consist of clinical measurements of patients, their genetic information, various other pieces of information that we might have. And we want to know, does giving them a drug induce the good response that we want, okay? Or what is the response of giving them a drug? But the problem is, so we might have all this information at training time, but at test time, when a new patient, say, walks in, we might only have their clinical data and not have access to their genetic data because of the costs associated with, say, genetic sequencing or some sort of other technological limitations. And so there is this structured missingness in the data set where a fixed set of measurements is actually missing. And because it's in a high-dimensional setting, there's no way that we can actually impute these values and somehow try and reason about treatment effects like that. And so can we work around this? Well, for this, we need an assumption, and the assumption that we make is that all the confounders that we have for estimating treatment effects are measured. So we measure them at training time and we measure them at test time. And then our problem is basically divided into two steps. The first step consists of learning a sufficient covariate Z, and then the second step is using the sufficient covariate that we learn to account for missingness. Okay, so for this I'd like to introduce some foundations in the form of something called the information bottleneck principle. Now this is a popular compression technique that exists in machine learning, where the goal of this approach is basically to compress our information X into some sort of representation Z while preserving information about some output or outcome Y. And this is often written as an optimization problem, where the optimization basically allows us to learn what is the most meaningful compression of the data that we have. And this is given by this equation over here. Now, lambda is a parameter that trades off our expressiveness about y with the compression of x. So the more expressive we are about y, maybe it means the less compressive we are of x. And the situation when we have the perfect information about y is obviously the case when we have no compression at all. In recent years, this information bottleneck has been extended to introduce neural networks to parameterize these two mutual information terms and to perform this compression. So basically, we have two neural networks, an encoder network and a decoder network with different parameters. And the nice thing about having parametric forms of these different distributions is then that we can use stochastic gradient descent to optimize the parameters and perform the compression. And this is basically analogous to various variational autoencoder approaches that have been proposed. The difference between the autoencoder approach and the information bottleneck is that instead of having outputs being X, we have outputs being Y. And instead of using the evidence lower bound and optimizing that in order to reason about Y, we now use this information bottleneck criterion. So the contribution of the approach that we propose here is really to generalize this information bottleneck approach to reason about treatment effects. And we do so specifically for missingness, which I will come to in a second. So our goal, as I mentioned, is to estimate the average treatment effect. So if we draw this as a causal graph, we can show that X are a set of covariates that we get, our input covariates, so our confounding variables in this case. Y is the outcome, and T is the particular treatment, where F of T is the regime indicator. In this case, it would be the observational regime, and Z would be our compressed representation that we want to learn, or our sufficient covariate. So rewriting the information bottleneck then for the causal setting, we end up with this kind of optimization problem, where we want to minimize the compression. We want to find the parameters that minimize this difference over here, basically. So compress X into Z whilst retaining information about T and Y. But remember, we said we wanted to infer treatments when data was systematically missing at test time. So we might be able to use the information bottleneck to learn a sufficient covariate, but if measurements are missing, what happens to those at test time? So the second part of our approach was really to account for that missingness by somehow doing some sort of distribution transfer. And in order to do that, basically what we do is we use something known as the Gumbel softmax reparameterization trick. So what this does is it basically allows us to learn a discrete representation of the covariates that we have to obtain equivalence classes between our training cases and our test cases, so that we can transfer the relevant information to cases where information is missing at test time. And once we perform this discretization, then it means that we can integrate over all possible values of Z, and in doing so we can then, because it's compressed now, we can reason about the specific causal effect, so the difference in the effect of the outcomes basically when you treat and when you don't treat in the observational regime, given the sufficient covariate. So what does this look like, and how do we actually do this in practice? Well, in practice, it consists of training two encoder networks, namely Q eta and Q phi, that are used to basically learn this discrete representation of the covariates, and then a decoder network that allows us to approximate these treatment effects based on the sufficient covariate Z and the treatment assignment. So in practice, this becomes optimizing this criteria over here, where this is the mutual information that's encoded by one encoding network. The second encoding network encodes the second mutual information term, and the decoder network accounts for the last term. So our encoder tries to minimize this or maximize this quantity, and our decoder network tries to adjust for that. And again, lambda is the Lagrange parameter that adjusts the degree of compression and controls the degree of expressiveness about Y. So in this case, we include this such that we can have a joint distribution and such that it's identifiable in practice. But what you could also do is you could force the treatments to be certain treatments that are given in your data and just observe the outcomes if you're only interested in the treatment effect, for instance, and you don't care about this distribution. So what does this look like when we actually apply it to different data sets? Well, we applied it to data from a randomized experiment, a control trial that was conducted to assess the effects of educational intervention and childcare on outcomes in terms of test scores for infant health and development. So our interventions in this case, our T are education, our outcomes are the test scores, and X would then be different measurements that were taken for the patient, or in this case the infant, and their mother. So maybe their birth weight, their health index, their sex, their head circumference, educational levels, birth measurements, other different factors. And this is a randomized setting. So because we know in this case that it's randomized and it doesn't have any confounding, what we can do is we can artificially introduce some form of confounding. And we can see whether we can recover the treatment effect and learn a representation of the true confounder based on this artificial injection of confounding. And how do we do that in practice? Well, basically we de-randomize the data by removing a portion of the treated group, so the treated children, and you can choose any sort of population that's treated. In this case, we chose to remove the treated children with non-white mothers. So we know in this case that ethnicity is the confounder. And when we do this bottleneck approach then, so if we perform these experiments, what we see is that we can compare our approach to various different baselines, such as using ordinary least squares regression, having a separate ordinary least squares regression for each treatment, whether t is 0 or t is 1, k-nearest neighbors, and various other benchmarks. And we can do this when there's no missing covariates and when there's 3 missing covariates. And overall, we see that our approach produces the most accurate estimates. So these are the errors in estimating the treatment effect. We have the lowest errors, so we learn the most accurate estimates of the average treatment effect. But what is the sufficient covariate? How do we know that we've actually learned a sufficient covariate, first of all? Well, going back to this scenario here that we assume, so the causal graph that we assume, we know that we have a sufficient covariate if conditioned on this variable, y becomes independent of ft. In the randomized control trial setting, we know that this arm is missing, so this A arm is missing. And why is that? Because the treatment is independent of our representation that we learn. The treatments are assigned randomly. So in this case, there should be very little information in this arm. So this mutual information term between I and Z, t, so between Z and T, should be almost flat. It should be stable for different values of lambda. And in the case of the de-randomized setting, where we introduce this confounding, we should be able to control this lambda parameter such that we can go from having a completely insufficient covariate to learning a sufficient covariate. And this is exactly what we see over here. So in the randomized setting, you can see that the information basically saturates at a particular point, and this is basically just, it's flat, there's no information. It's random, so there wouldn't be any information in that arm. And in the case where we have de-randomized and we've actually introduced this confounding, if we apply our approach, we can see in the beginning, so for a specific value of lambda, we can see that we have not learned a sufficient representation, but then we can also explore a range of solutions all the way to where we have a completely sufficient statistic of confounding. And then we can look at what happens over here, and we can see whether this representation actually makes sense for these particular lambda values. And that's what we do next. So we know that we have now a sufficiently reduced covariate, but is this representation interpretable? Does it make sense with what we know to be our ethnicity confounder? So it turns out that the representation is very interpretable, in fact. What we do over here is we basically plot the proportion of the different ethnic groups in each cluster that we obtained from the Gumbel softmax reparameterization trick. And the gray values are the de-randomized setting where we introduced our confounding, and the orange bars basically show the randomized setting where there was no confounding. So overall, you can see that the orange clusters basically show no sort of structure. They're very random. And the gray clusters seem to have more of a structure in this case. So if we look at cluster 2 in particular, there is a higher proportion of the African American population in this second cluster. So there's different cluster compositions when we de-randomize the data based on our sufficient covariate. And we can also compute these cluster-specific treatment effects, which allows us to personalize our interventions for a particular group based on their cluster or their sufficient covariate. But what's interesting here is that we find this enrichment of African American individuals in this cluster, which basically suggests that, and you also see a lower treatment effect for these individuals, which suggests that this is consistent with our de-randomization strategy, because it says that we observe a lower causal effect for these patients or these people in this cluster, but that we know we would expect that because we removed that group of treated individuals when we de-randomized the data in the first place. So we actually are able to recover the true confounder in this case. We can also do a similar sort of thing in a real-world application. Now, the difficulty here is that we don't really know all the confounders. We don't necessarily measure everything, but the approach can also give us insights into what might be the relevant confounders that we should condition on when reasoning about treatment effects. So in this case, we consider the example of estimating treatment effects in ICU patients that have sepsis, where our treatments are basically whether or not we administer a vasopressor. Our outcomes are measured in terms of the chances of them dying, so the odds of mortality, and our inputs are basically all the different vital counts of the patient, so their blood pressure, their heart rate, and various other temperature parameters and other measures. And what we see is that if we look at these clusters in terms of the sequential organ assessment failure score, we see that the clusters are very different depending on this score. In particular, we see that individuals that fall into groups that have, say, poorer individual SOFA scores or sequential organ assessment failure scores, they tend to have worse treatment outcomes in the long term. And this seems reasonable because we can see this information, but it seems reasonable because patients that go in worse have, so if they go into the ICU and have worse outcome, their organs are failing in the beginning, it's more likely that they are going to die in the long term. And so this is able to give us some sort of indication that maybe the organ failure assessment is something that confounds the treatments in practice. And so in conclusion, what I've presented here is an approach that basically learns a sufficiently reduced interpretable representation of confounding. We also show that it makes accurate predictions about the average treatment effects. What it also enables us to do is account for systematically missing covariates in practice. And by computing the specific causal effect, we can tailor our therapies according to that sufficient covariate or that group or cluster that the patients belong to. So we can have certain clusters receive certain treatments and other clusters receive other treatments. And so we can account for heterogeneity. Of course, this work lends itself to many different extensions and there's many different open problems. The first thing that we can think of is basically, can we introduce some sort of structure, so more structure into the representation that we learn of this confounding, maybe by introducing invariances in the latent space of this autoencoder approach or this information bottleneck. Something that's very interesting is the use of instrumental variables. So can we validate whether we learn a sufficiently reduced covariate by examining instrumental variables for this purpose? The third thing is, can we relax some of the assumptions that we made, the main assumption being that we have unobserved confounding, that we have observed confounding, and can we relax it to unobserved confounding? And then the last thing is, can we use this approach basically to evaluate existing clinical policies and basically guidelines that are currently used for, say, treating HIV and sepsis, and can we say how these would work in practice or sort of modify them and reason about the effects it would have on individuals and what the implications of this are in practice in healthcare. So with that, I want to say basically thank you for listening, and if you have any questions, please email us and get in touch, and we would love to hear more about your thoughts on this approach, maybe your ideas, your possible extensions, and if you're interested in collaborating. Thank you.